So let's define what a tree is. Why is that there? So definition, a tree. So it's a special type of graph that has the following two very simple properties. Is a connected graph that has no cycles in it as a subgraph, okay? That has no cycle subgraphs. Okay, that's all that it is. It needs to be connected and it needs to have no cycle among its vertices no matter what. So let's look at a couple pictures. The first is something we've seen before and certainly comes up in computer science and so on, is a simple binary tree. Let me just add maybe one more level here. So in a lot of ways, this is sort of like the quintessential tree. When you think of a tree, you often think of this tree here, but this is just one of many. I'll give it a name because a bunch of these trees do have special names. So this is binary tree. And you can talk about the height of this, right? I can continue to build it up. We've seen paths already in this class. Paths are trees, right? This is connected. It's very easy to see that this is connected because there's this long path here. Every two vertices lie on the path. So just a sub pieces of it is a path between X and Y. And it has clearly no cycles there. Here's another one that sort of resembles it. Let's draw it like this. So this has a special name, although I don't use it very often. This is called the caterpillar. What is a caterpillar? It's a path with like these additional like legs coming off of it, not necessarily the same amount from each vertex, right? If I turn it sideways, it kind of looks like a caterpillar. So sometimes we call it that. Here's another example. This is a star, right? This is a special tree where you have a central vertex of high degree and a bunch of vertices of degree 1 all joined to it. And then maybe one example that just doesn't have a special name, like trees can just look like whatever, as long as you don't have a cycle in them. And so on and so forth. Okay, so this is just some arbitrary tree. Okay, those are all simple examples of trees. What's not a tree? Okay, it's pretty simple, but anything that's not connected, right? That's not a tree because it's not connected. Remember, what's connected mean? There's one piece, there's one component, or more formally, for every pair of vertices, there's a way from getting from A to B. And that's clearly not the case in this example here, right? This vertex and this vertex, say, don't have a path between them. Okay, so that's not a tree. But even if you're connected, right, you might not be a tree. Say like this graph we've seen before. This is not a tree because it has a cycle. So that can't be a tree even though it's connected. So yeah, and it's one thing to like keep in mind, and we'll see this in the theorems that we state, and it'll come up later in the class, is that these two properties of being connected and not having a cycle are sort of like in contrast with each other. You know, very roughly, it seems like in order to be connected, you've got to have at least a certain amount of edges, right? You can't have, if you have too few edges, you're not going to be connected. You're going to have like these separated pieces. And as you add more and more and more edges to your graph, it seems more and more likely that you're going to get some cycle, right? It's like a denser structure. And actually that idea of when do you get a cycle or not is something important that we'll talk about later, maybe not about specific length cycles. But so yeah, they're sort of in contrast with each other. And a tree is sort of a minimal example of those two properties. Like it's a minimally connected graph and it's a maximally cycle-free graph, whatever that means. I'll restate that in just a moment here, okay? So this is the standard definition, but there's a bunch of other characterizations that we can use as an alternative to the definition. So I'm gonna write a theorem here and we're gonna prove like half of it. The rest of it is an exercise. So theorem, so the following statements are equivalent for a graph T. All right, so we fix a graph T. Let's draw that a little better. And the following 6 statements are all equivalent to one another. So what does that mean, all equivalent to each other? Like each of them holds if and only if the other holds. And it's a sequence of 6 of them. So I'm not just saying A if and only if B. I've got like a list of 6 here. So the first is just that T is a tree. And I'll just use, we defined this already. So tree is connected and no cycles, which we're taking as the definition. But once we establish this theorem that these are all equivalent, we can use any of these as the definition of a tree instead, if we like, okay? So the first one is that for every pair of vertices, x and y, in the vertex set of T, there is a unique path, unique XY path. Okay, so unique, this is the added thing here. We know that it's connected, so we know, like, so 1 begins to imply 2 because we know it's connected, so there have to be XY paths. But this number 2 says that there's one and only one XY path. There's not more than one. Once I write these all out, we'll prove a couple of them, but just to explain what's going on there, let me scroll up for a second here and just let's see if we can confirm that in our examples here. Like if you look here, this example, if I take 2 vertices on it, let me change colors here for these examples. Like if I take, you know, this vertex and this vertex, it's pretty clear there's only one way to get from A to B there. If I take like this one and this one, you look for a little bit, you have to go over here, across here, and then down there. There's only one way. If I take this one and this one, there's only one way. This one and this one, there's only one way, and so on and so forth. If I look at like this example, there's not even one way, right? Those 2 vertices don't even have a way. And if I look at this picture, well, yes, some vertices like this one and this one, actually, no, that's already a bad example, right? This one doesn't have a unique XY path, right? I can go here, or I can go here, okay? And then down this way. So this has 2 XY paths for this being X and this being Y. So that can't be a tree once we've proved it there, okay? So that's, yeah, this is actually like a really nice way of defining a tree, although it's a little less intuitive maybe than the first, okay? So let's continue to list these. Let me change over to black. 3 is that T, I said this already, but T is minimally connected. So what does this mean? What does minimally connected mean? What it means is that if I remove any edge, the graph immediately becomes disconnected, okay? So any edge removal disconnects. That's what it means to be minimally connected. It has as few edges as possible and is still connected. Okay, so if I have a graph T and any edge removal disconnects it, but it is connected, then it has to be a tree. Okay. T is maximal cycle free. So let me explain what's going on here. There's a few terms I haven't used before. Cycle free, I don't think I defined this term when I talked about subgraphs. If I say something free, it just means it doesn't have that as a subgraph. Cycle free means no cycle subgraph. If I say K10 free, it means it doesn't contain the complete graph on 10 vertices as a subgraph. Free is just a shorthand for saying not a subgraph. So no cycle subgraph. And maximal cycle free, what does that mean? Well, contrast it to minimal edge. It says that if I add an edge to this graph, I'm going to get a cycle. So add an edge without new vertex. I can't add a new. If I add a new vertex, I can avoid creating a cycle. So if I add an edge, then we get a cycle. Okay. Again, let's scroll up. I know these are not that difficult, but let's confirm 3 and 4 real quick. Minimally connected, maximally cycle free. Let's look at the trees here, right? So in this first one here, if I add an edge anywhere, you'll see that I'm going to get a cycle, because like there's always a way to get, say, from the top here to somewhere else, like here to here and here to here. So if I add that edge, I get a cycle just by like concatenating those 2 paths sort of to the top. Okay, in this path here, it's pretty evident, right? If I add like this path here or this edge here, I'm going to get a cycle. Same thing in all of these. If I add an edge, I'm going to get a cycle. Down here, this one, you know, if I add an edge here, I do get a cycle. If I add an edge here, I don't get a cycle. So this is not a tree because every edge should create a cycle. And then the other property was minimally connected. And I mean, I'm not proving this, but if I look at this guy, like say I remove that edge, clearly becomes disconnected. If I remove this edge, clearly becomes disconnected. If I remove this edge, it's pretty easy to see that it becomes disconnected, okay? These are just examples here. So when we'll prove this. Okay, I forgot to add something to the theorem, so let me add that real quick here. Let's say following statements are equivalent for a graph T on n vertices. Let's just say it has n vertices, just so we can make the 5th and the 6th statement a little bit clearer. And 5 and 6 are very closely related to 3 and 4, but they're not quite the same. So T is cycle free. Great, that's normal. We expect trees to be cycle free. And has n minus 1 edges. So here, this statement's a little more concrete than 4, right? It says that it literally has n minus 1 edges, and it's cycle free. That's equivalent to being a tree if we have n vertices. And then 6 is T is connected and has n minus 1 edges. Okay, let me scroll up so we can look at these all for a moment here. These 6 statements are all equivalent to each other. They're all the same. So you can take any one and prove any other and vice versa from them. We won't do, we won't prove all 6 choose, well, it's actually not even 6 choose 2, it's 6 times 5 different ways of ordering them and solving them. That's insane. We'll prove that 1 implies 2, implies 3, implies 4, implies 5, implies 6, implies 1. That will show that they're equivalent. Then you can follow the cycle and figure out, make one and follow from the other. It is a non-trivial exercise to actually try and take 2 random ones and show that they're equivalent, because some of them don't immediately easily imply the other one. You have to transform it, but it can be a good exercise. And also, I'm only going to do half of them. The other half are part of the homework, or they're an exercise in the book, which I'll probably end up assigning as a homework here. But let's at least prove a couple to get the feel for them here. So proof. Let's start off by showing 1 implies 2. Okay. So what's 1 and 2? We actually already talked about this proof a little bit, but 1 is that it's a tree. So we start with the fact T is a tree, so it's connected and has no cycle. Let's prove that there's a unique XY path for every pair of vertices, right? That's the goal here. Okay, so we want to show that there's a unique XY path. So as T is connected, there exists an XY path for all XY in the vertex set of T, right? We know it's connected, so there does exist an XY path. I want to show that there's not 2. If there exists 2 XY paths for some XY, then what? What can you guys tell me? What if you have 2 XY? So here's X, here's Y, here's one path. What can you tell me if I have a second path?
We have a cycle.
Yeah, we'll have a cycle. And here, to prove that there's a cycle, you kind of need to be a little more formal than I'm going to be. But just imagine, I'll explain it in words what happens. If I had the other path was completely independent of the first path, well, that's an obvious cycle, right? We're just looking at it. But the truth is, the other XY path may intersect the previous, right? It might go out here and then come back in, and then travel here and go back in, and then eventually end in Y. But what do we get in this picture here? Yeah, we actually got 3 cycles, right? So what you can say is the other XY path eventually intersects P. It may not intersect P till it reaches Y. It may intersect P just somewhere along the way. Either way, we're getting a cycle. Either way, this bit here is a cycle, which is forbidden. So if we have 2 paths or more than 2, we get a cycle, and that's a contradiction. So we have an XY path, but we don't have 2. So that implies 2. We have a unique XY path. Simple enough, okay? All right. Now okay, I hate when this happens. I have this pop-up that says, please move this window away from, because it's interfering, but I don't have any other window open. So if you guys can't see that, that's fine, but it does show up in the video. Do you guys see this thing this little pop-up here? You do. So yeah. I have no idea why it's there. I don't have another window open. Let's see. What if I slightly minimize the window?
It's not really that noticeable.
It's not that noticeable. Yeah,
it disappears sometimes.
It kind of fades out. Yeah, it's starting to fade out there. Yeah, I mean, luckily it's half of it's over the toolbar up at the top. So I'm just going to ignore it for now. But I had this come up in my other class, so I'll try and figure out a way to do this, solve it later. Okay, so number 2. But wait, no, not number 2. That 2 implies 3. This is an exercise, so I'll just say homework. It hasn't been assigned yet, but this is an exercise in the notes, okay? What about 3 implies 4? That one we'll do real quick. So let's just scroll up to check what 3 and 4 are. 3 is that it's minimally connected, and 4 is that it's maximally cycle-free, okay? Those two don't look immediately connected, Hey, Van, did you have a question? I see your hand up there.
Oh yeah, I was just wondering if we could just in a construction for the XY paths.
Yeah.
You just look at the symmetric difference of two paths when
Okay, that's
I'd always-
interesting. That's interesting. So like the symmetric difference of their vertices. So yeah, one thing actually this raises immediately a good question, is that, oh God, what's happening? Come on. That I wasn't, my illustration here wasn't as good as it should have been, because these two paths may also share edges with each other, right? Here I just had them only intersect in vertices, but it may go in here and then like travel along and come back out there a little bit. So
yeah, I think what'll happen is the symmetric difference specifically of edges
uh-huh.
will form cycles,
a collection of cycles, yes.
or be empty if it's the same path.
Be empty if it's the same path. Yeah, that sounds about right. Yeah, that may be a good way to do it. Absolutely. I think what I would say, I would name the vertices on P and then look for the one with the highest index other than the end where they share a vertex. And then I know that from here to here and from here to here, they don't intersect anymore because this was the highest index where they intersected. And so this on itself would be a cycle and nothing else. Yeah, Andy, what's up? You're muted.
What's a symmetric difference?
Yeah, so if you take here, I'll draw the Venn diagram of it real quick. So if you take two sets, the symmetric difference is just everything that's in one and not the other, and then in the other and not the one, right? So it's this and this, right? If you were taking sets, and you could do this with vertices or edges or anything like that. So it's union minus intersection is another way of defining it. In fact, it's great that I said in my other class, I didn't even define it because I don't usually talk about the symmetric difference because you can get it from smaller things, but it's sort of a mouthful to say. Yeah, anyway. All right. Okay, so 3, let's go back up. So 3 is minimally connected and 4 is maximally cycle free. This one's less clear, like what's the connection between the two, but let's work this one out. And this one's easier than it seems because again, we're not proving if and only if, we're taking 3 and making it imply 4. And later on, when we go through the whole cycle, we'll get that 4 also implies 3, okay? Okay, so, yeah, actually this is nice. So okay, I don't know why this keeps staying. Oh my goodness. Okay, somehow that fixed it. Okay, so let's start off with let X and Y be non-adjacent vertices in T. Okay, so I'm scrolling up again. I'm looking at 2 non-adjacent vertices in T. You might have to actually prove that such things exist. But let's just assume we've got 2 non-adjacent vertices. And 3 says that T is minimally connected, but actually all we care about is that it's connected. So if it's connected, there is an X and Y path. By the way, I did skip one other detail in this proof. Here I'm assuming I can even find 2 distinct vertices, period, right? What we actually need to do to prove this is throw out the case when n equals 1 initially, that we have a graph on at 1 vertex. But that's easy to check. You can check if you have 1 vertex, all these statements are the exact same as each other. They basically have no content. So we can assume that n is at least 2. In fact, you can assume n is at least 3 because the connected graphs on 1 vertex is just a single edge, and all of these trivially hold for that as well. Okay, all right. So we've got X and Y are non-adjacent vertices in T. So as T is connected, right? It's minimally connected, but we're not even going to use that property. You're just using it as connected. There exists an XY path. Let me draw the picture here. So we've got X and we've got Y, and they were non-adjacent in the graph here. They were arbitrary pair of vertices non-adjacent. There exists a path between the 2 of them. Now we're trying to prove that the addition of any edge creates a cycle, right? But what happens if I add the edge XY? So adding edge XY to T, by the way, I'll often write this notationally as T literally plus XY. That means the graph T plus the edge XY. So if I add in this edge here, what happens? I got a cycle, right? And this holds for any pair of vertices that are non-adjacent. So anywhere I could add an edge, I get a cycle by adding that edge because there already existed a way to get from X to Y, and putting on that edge, completed the cycle there. So this proves 4. I mean, because what does 4 say? 4 says that it's maximally cycle free. Adding any edge creates a cycle. I just proved that any edge will create a cycle. I didn't even use the minimally connected part of this to prove that. I just used the connected part of it. Okay. Oh, this is really annoying that this thing keeps doing this to me. Okay. Yeah. All right. 4 implies 5 is again a homework. And then 5 implies 6. What's 5 implies 6 here? Let's look at the statements here. 5 is that it's cycle free and has n-1 edges. And 6 is that it's connected and has n-1 edges here. Okay. So this is like an analog of 3 and 4, but kind of in reverse. And we're not talking about minimal and maximal. We talk about the number of edges here. So it's cycle free and has n-1 edges, or connected and has n-1 edges. So let's use the fact that it's cycle free and has n-1 edges and try and prove that it's connected. All we have to do is establish that it's connected because we know the number of edges here. Okay. So to prove this, we have to show it's connected. So suppose not. Suppose not. In other words, T is not connected. Okay. So if T is not connected, I don't know why that's staying up each time. Then T looks as follows. T has some components, right? Here's a connected piece. Here's a connected piece. Here's a connected piece. And here's a connected piece, right? Those are the components of the graph here. Each of these components, each is cycle free. Also, each is connected. But let's think about this for a moment here. They're each cycle free and they're each connected and connected. So what do I know about the number of edges in like this piece here? Let's call this piece like T1. So number of edges in T1. How many edges are in that? It's actually, yeah, someone unmuted was going to talk. Go ahead.
Is it supposed to be like like n-1 edges given that little component there?
Yes, it's one less edge than the vertices in that component. Okay. Why is that? Why is that? That actually follows from, that should follow from, let's see here. Oh, you know what? Actually, this is interesting. Are we using 1 here actually? So T is cycle free. What can we say? What can we say? Yeah, okay, actually I'm a little confused now here. I want to apply 5 in order to establish this, but I'm actually not seeing it anymore here. So 5 says, so we can assume that T, yeah, Van, Andy, I see both. Van, why don't you go first? I think your hand was up first, and then did you want to add something?
I was just thinking. Sorry.
Oh. Yeah, the hand is up there, right? But so Andy, maybe you had something.
I was thinking we could take a connected graph and then remove an edge and then add an edge to the non-disconnected part.
Okay, that's a nice idea. That technique will definitely be useful at some point in here. I don't immediately see it, so that may work here as well. But I want to do something. I want to use 5 a little more directly if I can.
Do we need to take into account that all these components are still connected? So there's supposed to be one edge going in between each component. And so if we say we've got 4 components here, we've got, T1 minus 1, T2 minus 1, T3 minus 1, T4 minus 1, and then you add in the edges again. So that way you're maintaining your fully just via T minus 1, since the edges in between cancel out.
Yes, yeah. So Colton, definitely that's what I'm going for to end the proof here, because what I want to say is just look at 2 components real quick, right? You can even forget the rest. We definitely have at least 2 components. So the number of edges in T1 is VT1 minus 1, and the number in V2, this one is VT2 minus 1. And now if I say, okay, what's the total number of edges in the graph in its entirety? It's this number, not more than this number plus this number. But I have a minus 1 twice, so the number of edges is going to be at most n minus 2, which is going to be a contradiction, right? So, okay, let's think a little more clearly about what we're doing here. We're trying to prove that 5 implies 6, and we're doing that by contradiction. So we're assuming that 6 fails. We know that we have n-1 edges because we can apply 5, and we're assuming it's not connected. So
Doesn't that like force a cycle? Once you disconnect it, you have to like put that edge into one of the components. So you get a cycle.
oh, I see what you're saying. Yeah, I mean, so yeah, that would work in order. Like, I just want to get a direct contradiction, and here this would be a contradiction. I'm just not establishing these two bounds at the moment. But you're right. Another way to actually see that would be, so you have to add an edge inside of one of these to actually get up, and that would give you a cycle. But yeah, I'm doing this a little bit roundabout way. Like, this is getting these quantities is not working for me right now. So let's like put a big question mark here. I want to be able to move on to the other topics. Maybe like that 5 implies 6 has now become a homework. So that homework got a little bit harder because I messed up. So anyway, we'll see. The last one would be that 6 implies 1. And this one was going to be a homework regardless. Okay. So this one here, there's a little bit of a question mark here. I got tripped up. If we have a few minutes at the end, I can come back to it. But I want to make sure I get through a couple more proofs here rather than continue on this one here. Okay. All right. So the next, we'll call it a proposition about trees just because it's a very short proof here. So every tree on at least 2 vertices has at least 2 vertices of degree 1. Okay. The existence of just one vertex of degree 1 is extraordinarily helpful when doing induction on trees, and we'll see it later. You can pull off a vertex of degree 1, and then you're still left with a connected graph with no cycles, and you can induct on that thing. This is simple, but let's go back and look at our pictures from the beginning here. Yeah, find a faster way to do this. So if you look at these pictures, this guy in the binary tree has a bunch of vertices degree 1 at the bottom level of the tree. The path here has exactly 2 vertices of degree 1, but we only asked for 2. The caterpillar has a bunch here. The star has a ton, right? All these like guys here. And then this tree here branched out into a bunch of vertices of degree 1. Sometimes we call these leaves, right? We like the tree metaphor. So a vertex of degree 1 is a leaf. Although a binary tree, as computer scientists often joke, is like written upside down, right? This is the root, and these are the leaves, like, you know. And the long-standing joke is that's because computer scientists don't go outside, right? They don't know what trees look like. Sorry, Jack. Like I say, you probably heard it before, right? So
I definitely have.
yeah. So, yeah. So, but those are the leaves, the vertices of degree 1. And now I can't. This interface is a little annoying. I can't like do what I want to do every time. But all right, that's fine. So those are leaves, and I claim that every tree has at least 2. And you can actually make a much stronger statement than this. You can predict how many leaves or how many vertices of degree 1 are going to be there based on the degrees of the other vertices. There's a nice like identity you can write out, which is worthwhile and maybe a good exercise for later. But what's the proof of this that we at least have 2? So you can kind of like try things like, well, if you can find 1, then like walk along it until you like terminate, and you can argue that that's got to be a vertex of degree 1. But let's use our max-min substructure technique here. So look at end vertices of a longest path. Okay, so we look at a longest path and look at the end vertices of that longest path. And we're working in a tree here, okay? So these vertices, what can you tell me about them? What do we know about longest paths when you look at the edges coming out of vertices here? What have we learned already that we've used a couple of times?
All of their neighbors are included in the path.
Exactly. So there's no neighbor out here because that's a longer path. So this doesn't happen. So all the neighbors have to go into the path. But what's that? What if I go into the path?
A cycle?
Exactly. I created a cycle. So you can't have this either. So how many edges can come out of this vertex here? Yeah, 1. The one that's already been illustrated here, and another one here. Okay, so this end vertex and this end vertex both have degree 1 in a tree, no matter what. And that's using the cycle free property mostly there. We are using connectivity as well to like get us a path. If you didn't have any longest paths, like you had no vertices at all, then you'd have a bunch of, you had no edges at all, you'd have all your vertices would be degree 0, so you wouldn't have this. Yeah, okay. So we're going to use this to prove a more interesting theorem. So let me see, do we have something after that too? Yeah, okay, we might be able to get through both. Okay, so this theorem is going to show when a graph contains a tree as a subgraph. Okay, so if you have a certain graph and it has a lot of edges, inside of it, you'll be able to find a tree subgraph certain times. So sometimes you're looking for a certain substructure, and you can always find it if you have enough edges here. This leads to an absolutely beautiful, very, very difficult conjecture that's stated in the open problems, like an improvement to this theorem. But this theorem's interesting in its own right here. Okay, so let T be a K vertex tree. So this theorem's less about the tree itself and more about the theorem that contains it, but just let T be any fixed K vertex tree. It could be a star, it could be a path, it could be a binary tree, whatever. Okay. Now, if G is an n vertex, actually, we don't need the number of vertices here. So let's say if G has average degree at least 2 times k minus 2, then G contains T as a subgraph. Okay. So if my average degree is high enough, the average degree is equivalent to knowing the number of edges, right? Because of the handshaking lemma, if I know the average degree, I can compute the number of edges out of that. So you can take this as a statement that if you have enough edges, you will get a tree of this fixed type, no matter what it is. In fact, because T is arbitrary and fixed in advance, this theorem can be stated in what sounds like a stronger way. It says that if G has average degree 2 times k minus 2, then it contains every single k vertex tree in it. It has binary trees, it has paths, it has stars. Every tree on k vertices you can imagine appears somewhere as a subgraph, as long as the average degree is high enough here. Okay. Later on, we'll actually talk about, in fact, probably starting next lecture, what we're talking about when I say all the different trees. Like, how many different trees are there? Like, you could sit down and try to draw a bunch of trees on 100 vertices. It would take you the rest of your life, but there's a certain number of them, and we can actually figure out how many. Here, I'm saying that if my average degree is high enough, I'm going to get all of them on k vertices. Okay. Keep in mind, this average degree condition guarantees that G will have more vertices than K. It better have at least as many as K vertices, because otherwise you're not going to have K vertex trees as subgraphs if you're not bigger. This having average degree here suggests you're already at least about twice as big, right? And in principle, much, much larger. Okay, so proof. So this proof's a little bit involved. It's not that hard, but it's kind of procedural, which is sometimes hard to explain here. Okay, so what I'm going to do here, the first thing we're going to do is, when you have an average degree condition on your graph, it's often useful to think about the subgraph that implies. Anybody remember the theorem from, I think we didn't finish it the first lecture, but the second lecture we talked about, if you have average degree something, it implies something about a subgraph. Anybody remember what that was? Even if you don't remember the exact statement, like what does average degree give you?
A path, which is a tree.
Okay, so that's true. We can build up a path off of minimum degree, right? But a path is a particular tree. So I'm not claiming I can find a tree of k vertices. I can find all of them simultaneously. So that'd find us the path, but I want to find all the others as well. There was another theorem about average degree that converted to minimum degree. Anybody remember that?
That it contains a subgraph with minimum degree greater than half the average degree.
Excellent. Yeah, Christian, great. Exactly. So by a theorem, I'm going to say, I don't have a number for it. G contains a subgraph H with minimum degree strictly more than 1/2 the average of G, so D of G, but we know what D of G is, so it's strictly more than k minus 2, right? That's 1/2, 2 times k minus 2. So H has a minimum degree, so let me just write minimum degree of H is strictly greater than k minus 2 k minus 2 is an integer, so it means it's just greater than or equal to k minus 1, right? The minimum degree is an integer. Average degree might not be an integer, but minimum degree is an integer. So if I know I'm strictly more than k minus 2, I know I'm at least k minus 1. I get that like free jump by 1. Okay, so I have a subgraph in it that has a nice minimum degree condition. And then Van's right, you can use this minimum degree condition to find yourself a path. In fact, I think we did that earlier. But again, that only proves the theorem for t a path. And we can do something more. I want to prove it for t no matter what t is.
Here we have a complete graph on k minus 2 vertices, right? Is that our game?
Not necessarily, right? So we know what the average degree is, but imagine k is like 12 and g has 10 billion vertices. All we're saying here is that the average degree is around 24. So it's quite a sparse graph. You know, it may be spread out a bunch, but we do have a reasonable, we have an average degree, and then you can squeeze it down, and that subgraph has a high minimum degree, but it may still be widely spread out. It may not be squeezed into a few vertices. So yeah, that's an important distinction, right? If you remember how this theorem was proved, it was by removing vertices of low degree. And you may only have to take relatively few steps in order to establish that. You may be left over with a ton of most of the vertices at the end, in principle. In fact, that's an interesting question, is how, to try and determine how many steps that procedure stops after. I don't actually know off the top of my head. It surely depends on the structure of the graph, but yeah. Okay, so what we're gonna do instead is basically work with H, because I'm gonna look and try and find this tree inside of H, and if I find it in H, then it's in G. I didn't state this, but being subgraph is clearly a transitive property. If I'm a subgraph of H and H is a subgraph of G, then the first thing was a subgraph of T, of course, right? So want to show T is a subgraph of H. And then I actually didn't use this notation. It's not uncommon to use this standard set notation here for saying H is a subgraph of G. Of course, this doesn't technically make sense because G is not a set. It's a pair of sets of edges and vertices, blah, blah, blah. But anyway, that's how we use that notation. So I want to find T as a subgraph of H. And I'm going to do this with the following procedure. Okay, so I want to enumerate the vertices of T in some fashion. So what I'm going to do is remove vertices of T one by one. Let's see, remove vertices of degree 1 of T, one by one. Okay, so I'm just gonna prune this tree. I've got this tree, I'm gonna find a leaf. I know it has at least 2 vertices degree 1, find one and pull it off. So let's look at a picture, because we're actually establishing a result here as well. So let's say we've got this tree like this. Okay, that's probably more than I need. And what I'm gonna do, is remove vertices of degree 1, one by one. So say I start with this vertex. If you have choices, just do it arbitrarily. I'm going to name this V1. That's the first vertex that I'm going to remove. Once I've removed that, let's make a couple observations. Does the graph remain cycle-free? Yeah, removing stuff never creates a cycle by accident, right? There's no way that can happen. Does the graph remain connected? Yeah, these graphs remain connected. Removing a vertex is not always safe. If I remove that vertex, I get 2 pieces. But if I remove a V1, notice what happens. It's kind of safe because chopping this piece off, this is gone now. So this can't be disconnected. Removing this edge is not safe, but when I remove this vertex, I get rid of the edge and the vertex. And so the rest of the graph is still a tree. Okay, so this pruning procedure is safe. So then in the resulting graph, I look for a vertex of degree 1 and remove that. So let's say then I remove V2, that was always, and then V3, and then V4. And now let's remove this as V5, right? After I've removed V1, 2, 3, 4, this vertex here is now degree 1 because its 2 leaves here got destroyed. So I removed it before I removed, say, this vertex here. Then V6, V7, V8. Now this one can be removed, V9. And then I'm gonna name this V10, even though once I got to this point, that actually had degree 0, right? I was ended with a single vertex that had no edges coming out of it. But my purpose here is to get an enumeration of the vertices. I listed them in order. And let's look at the consequences of that enumeration. Okay, so this enumerates the vertices of T as V1, V2, up to VK. VK. I call that V10. It was 10 vertex tree. Okay, so now all the vertices have a name. And let's make the following observation. Each VI has exactly one neighbor among where? Among which vertices? So think about this procedure. When I removed V1, it had exactly one neighbor. That neighbor happened to be V10, right? When I removed V7, it had exactly one neighbor, and that neighbor happened to be V8. When I removed V6, it had exactly one neighbor, which happened to be V9, and so on, so on and so forth. When I removed V5, it had exactly one neighbor, and it was V10. So where does the neighbor of VI live? So VI may have more than one neighbor, but it definitely has exactly one neighbor in some special subset of the vertices.
It's the greater indexed vertex.
Precisely, the later to be removed vertices. So it has exactly one neighbor among VI plus 1, VI plus 2, all the way up to VK. Okay, this actually only holds for I strictly less than K, because like I said, the kth vertex doesn't have any forward edges. It just dies out. But like, look, V1 has a neighbor among V2 up to V10, in particular V10. V3 has a neighbor among V4 up to V10, in particular V5, and so on and so forth. That was exactly this procedure described in a different way. So there's like one forward edge each time in this enumeration, which is really handy. So using this enumeration of the vertices, I'm going to embed this tree into my graph H. So embed each vertex of T into H to find T in H. So I'm going to try to create the tree T on the vertex set of tree H. So I have to maintain all the appropriate incidences in there. Okay. So how do I do that? So the first step is choose any vertex of H for VK. So I'm going to embed these in reverse order. So let me scroll up real quick in reverse order. So what I'm going to do first is embed V10 into my graph G. Just choose any vertex of H to be V10. That's going to be the vertex V10. Okay. And then I'm going to try and find V9 and then V8 and then V7 and then V6 and so on and so forth. I'm going to put those in one at a time, and I have to maintain this incidence property. Okay. So choose any vertex of H for VK. Great. Now, to embed VI, we need to identify the vertex VJ that is adjacent to VI, where J is greater than I, and VJ already has been embedded to G. Let me draw a picture to make this clearer, what's going on here. So here's H, right? And I'm working this procedure. I've embedded VK somewhere. Let's just work with K equals 10, since that was our example. So say I said, there's V10. And then in step 1, the first step, I'm going to put down V9 somewhere. Sorry, I haven't put it down yet. How do I put down V9? Well, I look at V10. It's got some edges coming out of it in the graph G. In fact, it's got at least K minus 1 edges coming out of it, right? That was by the minimum degree condition. Now, what do I know? If I look at my graph above, this guy here, V9 has to be adjacent to V10. So when I embed V9 into H, I better choose a neighbor of V10 in H to embed it to. So let me scroll back down here. When I do this, I better choose one of these vertices to be V9. Because if I choose like this vertex over here to be V9, then I'm not getting my tree, because V9 and V10 have to be adjacent to each other to establish the tree. So V9's got to be chosen from one of those. I'll just choose any one I like. Okay. Let me get rid of this guy here, that V9. Okay. So now V8. So now I can look at V9, and it's also got some edges coming out of it. One of those edges already goes back to V10. What was V8 adjacent to? I don't want to keep scrolling up. Can someone tell me, just based on if you have the drawing on your paper there, what was V9 adjacent to? V8 adjacent to? Was it adjacent to V9?
V7.
Okay, but what's the unique one among the higher indexed vertices?
What do you mean exactly?
Okay, so remember we established this thing here that each VI has exactly one neighbor among VI plus 1, I plus 2, I plus k. So if we go up here, V8 was adjacent to V7, but among the higher indexed neighbors, there's V9 or V10, it's adjacent to V9. So that's what I mean, the special forward one. I couldn't remember the picture. So V8 goes forward to V9. So what that means is that now when I choose the vertex for V8, it better be one of these neighbors of V9 in the graph H, sorry. So take that to be V8. And then V8 has some edges coming out of it. So far, we're just working on a path, so everything's fine. So here's V7. Now, what was V6 adjacent to? In the same thing, what was the forward edge it was adjacent to?
I think it was V9.
V9, okay, great. So now we kind of backtrack to V9 and say, okay, I want to choose V6. It should be one of these guys here. But now things get interesting, and they were already interesting. V9 has k-1 edges going out, but one of the edges went to V8, one of them went to V10, and it's possible one of these edges also goes to V7, even though we're not using it in our tree. It might be used up. So I'm hoping that I still have a free vertex here. Do I have a free vertex? Yeah, I do, because there's k-1 edges coming out, and each point when I'm embedding a vertex, how many things are there that, how many previously embedded things are there at that point? There's at most k-2. Sorry, does V7, V9 give a cycle? Yes. So Eric, that gives a cycle in H, right? So H has a cycle among vertices of the tree T I'm trying to find, but that's okay because I'm looking to find T as a subgraph. So I can just remove that edge when I'm trying to establish that it is a subgraph. Does that make sense? Yeah, okay, great. So yeah, absolutely. In fact, it could be that every single edge is present here. And then it's like, well, I have something much bigger than T, but I just want to find that T is inside of that somewhere. So I claim only k-2 things can be adjacent already to the VJ, okay? So remember, what am I trying to do? I'm trying to embed VI, and here's VJ. This is the general situation. There's VJ and it has some edges coming out of it. And I want to find one of these vertices to be free. So I'd like to put VI here, but I can't put VI there if each of these vertices has been used up by something else. But let's just do a careful count here. When I've embedded VI, how many other things are there that's embedded? In principle, as many as k-1 vertices have been already embedded. This could be the last vertex. But VJ sends out edges to what? It sends out edges possibly to everything else that's been embedded, but what does VJ not send an edge to no matter what? It doesn't send an edge to itself, and it doesn't already send an edge to VI because I haven't put VI down. So there's two vertices that are safe. VJ has, there are k total vertices, but two of which cannot be adjacent to VJ. So the fact that VJ has k-1 edges coming out means there's always a safe edge here, okay? I know this is a little bit hard to follow. It's hard to describe in a picture here. But it means that VJ always has a safe vertex to embed to. Doing this by induction might be a little easier or a little clearer in a written form, but I want to do this procedural way here, okay? So VJ is safe. That means like if I continue to do this picture, like I think, do we say V6 was next to 9? There's a V6 here. Then when I try to do V5, what was V5 adjacent to in the previously embedded? To 10 as well. Okay, so then we go back to 10 here and like look at 10. Like 10 had an edge going here, potentially an edge going to 8, to 7, to 6. But if you just check the numbers here, there's definitely going to be one still free, V5. This only really gets interesting when you reach the end of the procedure and I want to embed V1 somewhere, right? So at the last step, I want to embed V1. And V1, what was V1 adjacent to on the larger?
V10.
Was also V10, yeah. So when we get to the end here, let me just, recompute this thing here. So in this case, sorry, K is 10, right? Maybe I should have said that sooner just in our example here. K is 10. And we know that in H, how many edges are coming out of V10 in H? What's the minimum degree of H?
At least k-1, right?
Yeah,
because
at least, yeah, exactly. At least k-1. And in this case, since K is 10, we have at least 9, okay? So there's at least 9 edges coming out of V10. But there's V9, V8, V7, V6, V5, V4, V3, and V2 that it all might be adjacent to. But how many vertices could it be adjacent to? There's V2, V3, all the way up to V9 that this might already send edges to, right? But how many numbers are in this list here? There's 8 numbers in this list. Why is V10 not in this list? I said this already, but why is V10 not in this list?
It can't connect to itself.
Exactly, V10 is not adjacent to itself. So this is an instance where this doesn't work in a multigraph. We'd have a different situation. Why is it also not adjacent to V1 in this list? So they're adjacent in T, but why are they not adjacent yet in H?
We haven't slammed V1 down yet.
Precisely, I'm trying to figure out where to put V1, so it's not adjacent to V1 yet. So the point is, V10 might be adjacent to as many as 8 of the already embedded things in the graph, but it has 9 edges coming out. So there's definitely still one safe edge coming out, and that can be V1. But then I can't continue, right? If there was a V0 to embed, this rule would no longer work, because then it'd be like, oh, how do I embed V0? Maybe it's adjacent to V10, and V10 is adjacent to 9 other things already, and there's no free vertex. So that's why this like stops. And in this sense is sharp to highlight Van's question from previously. Like this theorem can't really be improved using this technique. The conjecture is that you can actually do even better here somehow, but you have to be smarter about this embedding, right? This was a greedy embedding. We just threw down a vertex and then just tried to find the next one, tried to find the next one, tried to find the next one. We didn't do any looking ahead to try and be like smart about it. Okay, so that actually ends the proof. All right, it's one of my all-time favorite professors would call this proof by example, because we kind of focused on the example here. So proof by example is not a proof, but anyway, if you flesh this out a little bit more, and keep in mind that we talked about this general J and I, this is a full proof here. Okay. All right. So I'm not going to prove this little theorem at the end, but I want to define one more term that we can wrap the lecture up here with. Okay. So a spanning. Let me write this clearer since I'm defining the term, and if you can't read it, it's not too nice. Spanning subgraph it's just simply a subgraph that uses every vertex of the original graph. So is a subgraph that uses every vertex of G. Okay, spanning subgraph of G. Okay, maybe it doesn't use every edge. G itself is a spanning subgraph of G, not too interesting, but there can be other spanning subgraphs of G. Maybe like, let's maybe just look at an example here. So like this graph here has the following spanning subgraph. Right, that's a subgraph of the left-hand side and every vertex is present there. This is actually a connected spanning graph. There are other spanning subgraphs that aren't connected. I could just take like the set of vertices. That's a spanning subgraph. Not a very interesting one, but it's like literally the vertex set. So that's what spanning set means. And what we actually usually care about is, so a spanning tree. Oh yeah, so why this term spanning? The vertex span the vertex. They hit every vertex. So a spanning tree, well, what's a spanning tree is a subgraph that's a tree that spans. So like the definition is like, it is what it is, but yeah, is a tree spanning subgraph, okay? This is a very interesting object to think about. Let me state a theorem here that we won't prove, although I'll sort of hand wave some ideas here real quick. A graph, I state this a little different than in the notes, but a graph G is connected if and only if it has a spanning tree. Okay, so this is a new definition of being spanning or not. You're connected if and only if you have a spanning tree. I'm not going to prove the whole thing, but I want to talk about the two directions for a moment here, just in the last like minute here. That it's connected if you have a spanning tree is easy, because suppose you have a spanning tree. How do I establish that I'm connected? Well, the tree is connected, right? Trees are connected, that's part of their property. And so I have a subgraph of G that's connected. Then G is connected, right? What's connected mean? You always have a XY path for every XY. The tree has an XY path, so just use the path in the tree to find the path in the G. There might be other trees, other paths, but this gives you one. So that's immediate. The other direction, that if you're connected, do you have a spanning tree? There's a few ways to prove this. One way is to just look at all the spanning subgraphs of G and show that the smallest one is a tree, right? Then that actually follows from some of our tree characterization theorems, okay? Another way to do this procedurally, which is actually better, is to build up a breadth first or depth first search of your graph. Grab a vertex and perform breadth first or depth first search. If you're connected, this procedure will stop and it will produce for you a tree. These two in principle are two distinct trees, okay? I gave a statement of I think was it breadth first? I don't remember. I stated one of these algorithms in the earlier notes. I haven't actually talked about it here, but this is one way to this confirms the theorem as well, and it actually finds you a spanning tree, okay? And we'll find out that having a spanning tree in a graph is super useful for, again, ordering the vertices in some fashion. If you have a spanning tree, then you can enumerate the vertices using the procedure we talked about above, and that can be handy. Even though not all the properties transfer to the graph, it can be a handy way of like talking about what does the graph look like, okay? But anyway, spanning tree is equivalent to whether you're connected or not, okay? Just again, with this depth and breadth first search, when your graph is not connected, if you perform BFS, you'll stop and there'll be some unvisited vertices, right? And so it's not connected, but then your tree that you built with BFS won't be spanning because there were some vertices left out of it, okay? Anyway, so the proof in the book is very simple. Or in the notes, you can take a look at that, and yeah, but I think I'll stop there.